Hello friends, in the last video I promised you that I will prove that this centripetal acceleration, that acceleration acting on a particle performing uniform circular motion, it is really radial. Okay, let us try and prove that. Okay, I'm going to draw a diagram, and we will be doing little geometry, little maybe trigonometry and little calculus. Okay, but then it is going to be very interesting. This is my circular path. Okay, the particle moves with angular velocity omega. Okay, this is my x-axis, and of course this would be my y-axis, right? Now this particle is performing uniform circular motion. That means its speed along the circular path is constant. Okay, at any instant, at any given instant, the particle is at point P. Okay, I am going to mark the position of this particle as P here, and coordinates of P I will take. Since I am taking x and y axis here, I'll mention the coordinates of point P here. Okay, let us imagine that the particle was initially at origin, let us say at point A over here, as I always call it, and in time t, it has moved to point P, and the angular displacement which happened over here is theta. Okay, now this has happened in time t, correct? So what can I say about omega? Can I say my omega is equal to theta upon t, or would it mean that theta is equal to omega t? That is fair, right? Now about coordinates of point P. Okay, I want to know what is x and what is y in terms of angle theta here. Okay, so I'm going to do some trigonometry. Yeah, so I draw a perpendicular here and a perpendicular here on y-axis. Okay, so one on x-axis, one on y-axis. Let me call this point M, and this point is N. Okay, and obviously this is 90 degree. So can we not say that this distance between O and M, that is my x, and it would be if radius is r, then it would be r cos theta, and this would be r sin theta, correct? Y equal to r sin theta. I am going to write that down over here. So x is r cos theta and y is r sin theta, correct? What are x and y? As the particle moves from point A to point P, the displacement along x-axis is x, and that is equal to r cos theta, and displacement along y-axis is r sin theta. I am going to replace this theta with that omega t. Okay, so that I want this theta in terms of omega t, I want theta in terms of time, right? So that I am able to differentiate with respect to time to get velocity and acceleration. Okay, so my x is equal to r cos omega t and y is equal to r sin omega t. Okay, I want to find the velocity now. X is the displacement along x direction and y is displacement along y direction. So if I differentiate displacement along x direction, I will get x component of velocity, isn't it? So I would say Vx is equal to dx by dt, and that would be equal to, now my radius is constant, r is constant, omega is constant. Okay, and then I will have to take derivative of cos omega t, which is going to be minus sin omega t, but then again you will have to multiply by omega, right? Chain rule. So it would be minus r omega sin omega t, correct? Now my velocity along y direction. So for that I'll differentiate this, and then my Vy would be equal to dy by dt, derivative of sine is cos. Okay, but still that omega t is there, so I will have to multiply by omega there. So my it would be r omega cos omega t, correct? Okay, now here you would be able to see that my velocity is tangential, right, and the particle is moving in anti-clockwise direction. So I'm going to mark my velocity over here as this. So this is my velocity. If you see here, my x component, okay, x component of velocity is minus r omega sine omega t. Okay, so it's like this. This is my velocity, and x component is negative and y component is positive. So vy and vx. Okay, so that is fine. Now I want to get acceleration, linear acceleration. So what do I do for that? I will differentiate velocity, isn't it? So if I differentiate vx, I will get acceleration in x direction, and when I differentiate vy, I get acceleration in y direction. So my ax is equal to dvx by dt, and that is going to be, now here r omega sine omega t, I have to differentiate that. So it would become minus r omega square cos omega t, correct? Similarly, my ay is going to be equal to dvy by dt, and that would be equal to, now here it is cosine, so derivative of cos is minus sine, so it would become minus r omega square sine omega t, isn't it? Now one thing is there, r cos omega t, r sine omega t, r cos omega t, r sine omega t, correct? So can I say that my my acceleration, x component of acceleration is equal to minus omega square x, and this is minus omega square y, correct? Minus omega square x and minus omega square y. All right, now so that means when this particle is over here, okay, it has got x component of acceleration, it's negative, and y component of acceleration is also negative. So that means my acceleration is going to be like this. Okay, so it is ax and ay. I'll put vector sign over there so that it is clear. All right, now let us do one more thing. Okay, here if you look at this triangle OMP, okay, theta is the angle, and if I find tan theta, it is equal to y by x, so it is PM upon OM, so it is y by x, correct? I have done that. Okay, there is some purpose to that. My acceleration is vector. Okay, I want to find the direction, and for that direction I need some angle with respect to x-axis, isn't it? So how do we get acceleration angle or direction of acceleration? What I will do is I want this angle, maybe either this angle or that angle. Okay, and when I complete this rectangle here, okay, this is the resultant of ax and ay. Okay, so my a would be equal to root over ax square plus ay square, where I get the magnitude, and for direction, if I call this angle alpha, then alpha would be equal to, now this is ay and this is ax, isn't it? So this is x, this is ay, so that would be I would say tan alpha would be equal to ay upon ax. Okay, ay upon ax. Okay, if I substitute this ax and this ay, so would it not be, see, omega square is going to get cancelled over there, correct? So it would be y by x. Okay, and what is y by x? Y by x is tan theta. So I can definitely say that tan alpha is equal to tan theta. That means angle alpha is equal to angle theta, isn't it? So in which direction the acceleration is acting? It is acting like this. So if this is theta and this is also theta, which was alpha over here, okay, so and alpha is equal to theta, so that means my acceleration is acting in this direction. So it is acting along the radius, right? It is proved here. Okay, acceleration is acting along the radius and towards the center, correct? That means it is center seeking acceleration. That means it is centripetal acceleration, correct? So it has been proved. Let us see what is the magnitude over here. Okay, if I substitute for ax and ay over here, would it not be omega square multiplied by, now over here, what is this, r square omega square r omega square cos omega t the whole square, that would be r square omega raised to power 4 cos square omega t plus r square omega raised to power 4 sin square omega t. You take r square omega raised to power 4 common, and cos square omega t plus sin square omega t is equal to 1, isn't it? We have that identity, right? So that means my acceleration is going to be, when I take it out of square root sign, it is going to be omega square r. Isn't it what we proved in the last video? Correct? My acceleration is equal to omega square r, or my acceleration can also be v omega. Okay, my acceleration can also be called as v square upon r, right? So it proves that yes, this acceleration is center seeking. Now I am going to give you one example here. Okay, I have a string and a stone tied to the string. Okay, what I do is I want that stone to whirl in horizontal circle. Okay, so I am whirling that stone in horizontal circle like this. Okay, just imagine, just try to visualize what you would feel. Okay, for that stone to continue that circular motion in horizontal circle, you have to continuously pull the string, don't you? Right? The moment you stop pulling the string, what would happen? The string will become slack and the stone would fall down. So it won't be able to perform that circular motion, isn't it? So there has to be tension continuously acting, and tension of that adequate value, in that string. Unless you have that much tension in the string, circular motion will not be possible. And that is why we say that centripetal acceleration is necessary for circular motion, and then centripetal acceleration is there. See, whenever there is acceleration, there has to be certain force, isn't it? That force is that tension, and that force, that tension is providing necessary centripetal force for circular motion. Correct? In the next video, we are going to talk about a few applications of circular motion, like banking of roads, and maybe we can even talk about vertical circular motion, right? Thank you so much.